そうですか。じゃあ最初から。Hello everyone, my name is Daisuke Nishino, and I am a member of China development team, and I have been working on visualization of China. So today I'd like to talk about a part of visualization and implementation. As the external specification is not determined yet, I'd like to talk about the internal of the visualization implementation. This is a brief self-introduction. I was born and grew up in Shizuoka Prefecture. I grew up watching Mount Fuji every day. I studied in Tokyo Institute of Technology. In undergraduate course, I majored in physics. Specifically, I studied high energy cosmic rays. And after graduation, I worked as a software engineer for a few years. And I entered the master's course of Tokyo Institute of Technology again. And in the master's course, I majored in computer science. I wrote a thesis on speech recognition. And after that, I joined Canon, and I worked as a researcher and software engineer. Specifically, I worked on face recognition technologies, and I developed surveillance camera software. And this February, I joined PFN. About my hobby and favorites. In my childhood, my interests were like this. As for sports, I played baseball and tennis. I played baseball for 7 years. And but I was not good at baseball, but rather than baseball, I liked tennis. I did not play tennis regularly, but sometimes I played with my friends, and I liked it. And when I was a child, I wanted to be a comic book writer. I wrote many stories in a series named Quicken no Bouken. And also I liked astronomy. That's the reason why I majored in physics at university. And programming is also one of my hobbies. I can't say I'm good at programming in this company, but I love playing around with these languages. For example, C++, Python, and JavaScript. In the past, I used to love the technologies behind .NET framework from Microsoft. I used to contribute to Wikipedia in the past. Translation from English articles to Japanese articles. As for literature, Miyazawa Kenji is my favorite author. He is a children's literature writer. He advocated self-sacrifice attitude for socially weak people. And as for music, I like classical piano solo. Especially I like Fujiko Hemming's interpretations. And this is also one of my hobbies. I'm a novice photographer, and I like to be a novice in the future because if I get scared, maybe I will get more serious for photographing. So maybe it's more fun to casually. So yeah, I like to keep being novice. And as for subject, I love to take photos of living things like birds, insects, and flowers. And I started volunteer activity when I was an undergraduate student, and it's now one of my main hobbies. I'm currently working at a self-study room called Medaka no Gakko for 3 years. The activity is to study, chat, and play with children. There are two key philosophies in this room. One is no distinction between students and staff. The other is no compulsion. So we won't enforce children to study. So basically, it's like we're friends rather than teachers and students. And in this activity, sometimes spontaneous events are held, like cooking class and some electronic works. And I hope in the future, I'd like to teach China for children in, for example, China playground for elementary school. And currently, the smiles are the primary motivation of my life. So I'd like to start the main topic. First, I'd like to talk about the background. As I said, I worked as a China developer, and I have been working on a visualization for some time. The background is in deep learning frameworks, there are increasing demand for computational graph visualization. For example, TensorFlow has TensorBoard, and Activists has been released from Facebook recently. Compared to these frameworks, China is relatively behind in this aspect. The difficulty is that China takes define by run approach. In define by run approach, computational growth can be defined every iteration. So to offer meaningful visualization for users, it's necessary to merge different computational graphs across iterations. So this is the topic of this talk. This slide shows what is graph merging in computational graphs. The left side of this slide shows the different computational graphs in different iterations. The left graph is the computational graph in iteration 1. And this one is that for iteration 2. In this figure, a pair of nodes with the same letter, for example, this x1 and this x2, have the same logically identical nodes, I mean variables. Because they are in different iterations, physically they are different objects, different variable instances, but logically they should be considered identical. The difference between these two graphs are the second node. This indicates a function, f1 and g2. In iteration 1, f1 function f1 is applied to x1, but the iteration 2, function g2 is applied to x2. So what we want is to merge these two graphs and generate this visualization. In this graph, logically different nodes are displayed in different nodes in this graph, but logically identical nodes, for example, x1 and x2, and y and y2, and h1 and h2, visualized as the same nodes. These two paths combine to one single path. So this is what we want to achieve. Let me start from some skills. I'm not an expert on graph algorithms, so possibly the algorithm I present here might be not optimal. So any advices for improvements are always welcome. And the algorithm and implementation are not final and susceptible of change before release. There are key assumptions on this application. The first thing is the most important thing in my view, that in most iterations, no new nodes or edges are created, because most commonly they are only created in the first iterations in almost all networks. In the rest of iterations, computational graphs usually simply traces the one in previous iterations. So the point here is the performance focus should be placed on tracing the existing graph rather than creating new nodes. So it might be okay that creating new nodes or edges are not at the best performance. And the second assumption is the chain computational graph is DAG and it's backward. That means it can be traversed from output nodes to input nodes. This is a simple example of how it works. This example is from the previous one. And what we'd like to do is to generate this merged graph from these two computational graphs from each iterations. In the first iteration, it's trivial. We can just copy the structure of the computational graph to generate merged graph. I'll skip the detailed explanation here. And the iteration 2, we have this merged graph from previous iteration, and we'd like to merge this computational graph. And we have to match these two graphs. Matching process starts from the output nodes. These two output nodes are known to be identical because they are output nodes. So make a matching node from these two nodes. And second, this is trivial because this is the only possible path from the output node. So this can be another node, matching node. And this. And the next, the function g does not exist in the previous merge graph. So we need to make a new node and node with this new node. And finally, the last input node is matched and added to the matching graph. So this is the matching process. And next, we can apply this matching graph to the previous merged graph and generate this merged graph. So the overall overview graph merging process is like this. First, chainer user code defines the computational graph of each iterations. And using the previous merged graph and this computational graph, we perform matching between these two graphs and generate matching graph, which is each nodes of this graph is a pair of nodes of computational graph and merged graph. And second, apply this matching graph against this merged graph and generate the new merged graph. This is the basic procedure of this algorithm. And each matching process in each node has three possible types of moves. For example, say we are going to merge this computational graph against this merged graph. And assume we are here, y, we are at y. And we'd like to find the corresponding edge or and node to this function f dash. The first candidate is to trace the existing edge. In this case, fa is compatible with f dash, so the one possibility is to just follow this path. This is the most, this is the lowest cost move in terms of graph complexity. And the second is the to create an edge toward the existing node. This is the second lowest cost in terms of complexity, and because we have to make one extra edge to the merge graph. And the last one is the most highest cost move. That is to create a new node and make an edge towards the new node. This is the most highest cost because we have to make one node and two edges, because this edge and this edge is also required in the future traversal. So there are three possible moves in matching node search. And as I said before, the most important thing is to obtain the best speed in the most common case. That is to simply trace the existing edges of existing graph. So the approach is to always examine the existing edge first and search into move in depth first manner. For example, we'd like to merge this computational graph against this merge graph, and so in this moment, the best move regarding the cost is to trace this edge, as I said in the previous slide. And the second move, assuming we moved here, is to follow the second edge here. So finally, we moved here. This is the input node, so we reached the solution. So in this case, just following the optimal move in each iteration achieve the solution in the fastest way. But of course, greedy approach is not always optimal. For example, assume this situation. This is the computation graph, and this is the previous merge graph. And we'd like to graph against this one, and assume we are at node E. The best approach, I mean the most low cost approach, most low cost move from here is to trace this edge toward D because they are identical. But that leads to this graph in the end because next we have to make an edge toward A. So this edge is required. And when we want to traverse a node D2, we have to make a new node D because this node is already used. And from this node, we have to make edge toward node C. So the final merge graph would be like this. In this case, 3 new edges and 1 new node are created. On the other hand, if we create a new node D when we are traversing this node, the final graph would be like this. Because from these nodes make a edge toward A like this. But when traversing D2, we don't have to create any new edges or nodes anymore. So the final graph will be like this. In this case, the new edges is 2 and a number of new nodes is 1. So in terms of a final graph complexity, this is a optimal solution. So how to minimize the merge graph complexity while taking advantage of greedy depth first search? And the solution is to place a limit on the number of new nodes and edges in each traversal in graph matching, and iteratively losing the limit until a solution is found. A solution is so solution is assured to be exist if we don't have a limit on this number, because if there's no limit on number of new nodes and edges, we can just copy the structure of the computational graph. So always solution does exist. So flowchart is like this. Start with the limit of new nodes and new edges, 0. And matching with this limit. So in most cases, I mean, if the merge graph has enough nodes and edges from previous iterations, almost all cases, the solution is found in this n equal 0 case. But if the solution is not found, we have to create a new extra node. So increase the limit by 1 and repeat the matching with this new limit. And in this way, the lowest complexity graph will be achieved. This is a basic idea. And I'd like to talk about the function with multiple inputs and outputs. Previously, I only talked about a function with one input and one output. But if we have multiple inputs or outputs, we have to some treatment. If there are multiple outputs, traversal proceed to X only if both output edges or not B, F are fulfilled. So only if these two edges are fulfilled, we can proceed to this node. And in the case of multiple inputs, we have to traverse each input sequentially. So in this case, from node F, first we take the path toward X, and rather than traversal to Y now, we have to going further in this path, and only if we found a solution in this path, we traverse towards node Y, and like this. And if both paths have solutions, this entire graph can be said to have solutions. The explanation of algorithms is that's all of algorithms. Here, I like to talk about how to designate a graph. A user needs to specify a range of computational graph. Range is specified by input variable and output variable. This is an example of designating the graph, subgraph. In this example, variable X and Y are defined. And this is this context is designation of a graph. Here, a user has to specify input variable as the first arguments, and a function definition follows, and finally, user have to specify the output variable too. And basically, matching algorithm automatically find logical node pairs, but user can manually designate a logical node by manually putting a tag to each variable. This would enforce logical identity of variables across iterations. And a user can also specify nested subgraph. Example will be in the next slides, but user can visualize hierarchical graph structure by nested subgraph. And also, If trainer extension is used, links are automatically visualized as hierarchical graphs without explicitly specifying subgraph. This is the simplest example. This one is the same as the previous slide. First, linear functions apply to these two variables, and sigmoid functions apply to the output of linear function. The output of graph visualization is like this. And the second example is to demonstrate the computational graph merging across iterations. In this example, this is just a toy example, but in the first iteration, plus one operation is applied to the input variable x. But the second iteration, the different operations are applied. And third iteration, also different functions applied to the input variable. And in all of these linear function is applied to the output of these operations. And the output resulted visualization is like this. As you can see, different operations in different iterations were merged in single graph. And this is the example of loop. User have to specify a tag to variable, as I said before. This line put a tag, and so by this line, each different instance of a variable will be treated as identical logical variable. So resulted merge graph will be like this. In this graph, variable h is visualized as a single variable. And this one is example of using trainer extension. By applying the extension like this, the implementation automatically find the links in the model and automatically construct these subgraphs like this. This is output from MNIST example from GNR repository. 3 links of linear operations this visualized as subgraphs. That's all of today's presentation. As I said, the external specification is not determined yet. So if you have some suggestion on features, please let me know, or some other members, or maybe you can post an issue to GitHub issues as a suggestions. Thank you for attention. Any questions? The question is, if there's a loop like this, the a new node creation algorithms can be applied or not, because it assumes that the graph is dive. So the answer is, the assumption is that the input computational graph is dive is the assumption. So I didn't assume the generated graph is acyclic. So I think it can be applied because the computational graph is still acyclic. I think so. Any other questions?
I'm wondering if you want to support it in different levels of abstraction. So you have these hierarchical subgraphs, but when you sort of label it as one node to make the graph look more simpler. For example, in a RESTnet, you have each RESTnet block to be visualized as one node.
Sorry.
I mean, so now the graph, if you visualize RESTnet, for example, the whole graph would be very complex. Right?
Sorry. Do you mean some example in the slide?
No, I mean, you know how RESTnet is.
Yeah.
So each RESTnet block is actually quite complex.
Yeah.
But most papers just visualize them as one simple node.
Yeah.
I'm wondering if you can have this abstraction here also. To help the user understand more easily how the computation goes.
Using extension, links are automatically constructed as subgraphs. So these graphs can be visualized in a simple manner. So, sorry, what's the question?
Yes, it's a purple rectangle on your slide now. That's a subgraph.
Yeah.
So you have a switch, you can just make this into one green number.
Reorder.
Can you visualize this in a simple manner? I'm just wondering if this is possible.
So he wants to reduce the subgraphs on the without rendering.
Yeah. Actually, by default, subgraphs displaying one node, and we can dive into the node and expand the subgraphs like this slide. Okay, thank you for listening.